All right, it's my pleasure to introduce our next speaker. This is Professor Bob Waymouth, who's also in the chemistry department here at Stanford. He's the PI of the GCEP program, Electrohydrogenation, Enabling Science for Renewable Fuels. Bob, it's all yours.
Okay, thanks, Tom. And I'd like to thank Sally and Richard for the opportunity to tell you about some of the work we're doing in our group, really to try to address what are some of the key chemical steps and what are the key things that we don't understand about solving this problem of activating CO2, taking electricity, converting it to useful fuels, or if we have fuels, how do we convert those efficiently into energy? So you heard this morning, since the dawn of the Industrial Revolution, access to cheap energy has both spawned and sustained the Industrial Revolution. And so all modern economies are based on the fact that we have both access to fossil fuels, which we are incredibly good at pulling out of the ground, and catalytically transforming those raw materials both into fuels and to all of the feedstocks that are the entire chemical industry. This has been a great run for 150 years. It's remarkable the expansion of opportunities that have happened and the degree to which economies have expanded because of this capability. But the question is it a sustainable model? And we heard today that we're engaged in an experiment on the test tube of our planet, and we're not quite sure how the experiment's going to come out. So for the past 10 years, our group has been starting to think about what is the science we need to understand to free us from the tyranny of our reliance on fossil fuels. Now, it's not completely a tyranny, it's been a benevolent dictatorship, but really, what are the challenges here, either if you have renewable resources as a source of liquid fuels, how might we use those more efficiently, both to power what we need to do, or to provide the materials and chemical feedstocks that we need? Or, inspired by GCEP, how could we take renewable energy, either from sun, wind, nuclear, however we get electricity, and turn it into a transportable, storable, convenient source of energy? So that's the challenge we've been working on, and you heard a very nice talk from Matt about that as well. So part of my group works on materials and feedstocks and catalysis challenges, but here we're after this business of synthetic fuels, and my colleague Chris Chidsey has helped me think about that in terms of what you might call an electron economy. So what is a liquid fuel? From first principles, if we teach our freshman chemistry class, these are high free energy electrons stored in chemical bonds. And nature's provided us with an abundance of them that we're running out of, and we ultimately want to convert those high free energy electrons into work. And the way that we do it for the last 150 years is we burn stuff. That's not a very efficient way to take the precious resources we have and do the work with it that we want to do. Moreover, if we have sources of energy, we'd like to take these free energy electrons, dump them into CO2 and water, as Matt pointed out, and turn it into a liquid fuel. And the fact of the matter is, despite the fact that we've been trying to do this for a long time, we still don't understand how to mediate these multiple electron and proton transfers. And we've also known since the time of the invention of the internal combustion engine that if you could do it in a fuel cell, it would be a more effective way to convert energy than in an internal combustion engine. So a fuel cell, as you note, if you take hydrogen, the simplest case, what does a fuel cell do? You need a catalyst to rip the electrons out of hydrogen, push them through a wire, do some work, and then dump them into oxygen. Or if you're doing this efficiently, it means that you can run it backwards like a battery. You could take electrons, rip them out of water, and dump them into protons to make hydrogen, or dump them into CO2 to make hydrocarbons or other types of fuels. So actually GCEP, the last 10 years, Sally gave a really nice summary of what's happened here. But a really exciting thing that's happened both in the chemistry and chemical engineering department is at the time GCEP started about 15 years ago, there was very little activity in electrocatalysis at Stanford. And now, largely because of GCEP, and with Tom Jaramillo, who you heard from, Jens Norskopf, Matt Kanan, who you just heard from, and a bunch of us in chemistry, we've all been stimulated to start to think about these problems. And there's really a very exciting community now talking about this in various ways. So hydrogen is one way to do this, but hydrogen's not a very efficient fuel. If you wanted to take electrons, as Matt just pointed out, actually the thing you would really like to do is to make gasoline. You'd take electrons and you'd pour it into CO2 and you'd make gasoline because there are few other materials on the planet that have an energy density that matches gasoline. If GCEP exists for another 10 years, we might be able to tackle that problem. But like Matt, what we've started to think about is one that's a little more tractable. Can we either take alcohols, which you might get from biomass, efficiently convert them into energy, or convert CO2 into methanol? And our approach has been to really try to understand in chemical detail what are the scientific challenges to do that. Now we can do it with hydrogen, so you can take energy and store it into hydrogen, but hydrogen has got a very low energy density. Nevertheless, with platinum, this works very well. There's probably not enough platinum on the planet to do this as much as we would want, even if we could develop a hydrogen economy. And for almost any other fuel, we can't do this very well. And one of the problems with CO2, Matt alluded to, it's an intractable little beast. It is not typically very reactive. It's thermodynamically quite stable. It's also kinetically quite inert. And if you simply try to dump an electron into CO2, you have to go to about minus 0.2 volts to do that. You're wasting a lot of energy to put that first electron into CO2. You don't want to do it that way. Secondly, if you had methanol as a fuel or any alcohol as a fuel, platinum is extremely good at stripping all the hydrogen off of methanol, but then once you're at CO, it's typically very challenging to oxidize that and to rip the electrons out of bound CO. So we need a different way of thinking about this, and we can't do it this way. And these are really very simple reactions on paper. And what we need, as Matt pointed out, is we need, but they're not very hard to do. So thermodynamically on an energy scale, converting CO2 and hydrogen into methanol is not very difficult thermodynamically. And in fact, to methanol, it's downhill. The challenge is it's not very fast. And here's where catalysis comes into play. We need a catalyst that will lower the barriers to interconvert these things so they happen very rapidly. And we want them to happen on the order of about 1 per second. The fact of the matter is, Matt alluded to one, there's basically not many catalysts that will do this at all, even with hydrogen, at a rate of about 1 per second. Secondly, the potentials at which you want to dump electrons and protons into CO2 are at the same potential to make hydrogen, and you would like to put all of that protons and electrons into CO2 and not make hydrogen. So that's the selectivity problem. This is the rate problem. So our approach has been to say, let's try to identify catalysts that we have from the literature that do these kind of reactions rapidly. And then if we can identify those catalysts, understand how they work, then we can induce those catalysts to behave as electrocatalysts instead of chemical catalysts. And so one paradigm we've been using is we identified a class of what are called transfer hydrogenation catalysts as an intriguing starting place to do this. And the reasons are the following. One, transfer hydrogenation is a mechanism of taking carbon-oxygen double bonds and reducing them, but you don't use hydrogen. Use alcohols as a source of hydrogen. So in these reactions, hydrogen's not generated. You don't need hydrogen to do it. And so they are not generating hydrogen while they're performing this reaction. Secondly, this reaction, if all the R groups are the same, is thermoneutral. What that means is the equilibrium constant is 1. These reactions are happening at the thermodynamic potential for oxidizing an alcohol or reducing a ketone. So every intermediate in these catalytic reactions, if these catalysts are operating really fast, all of the catalytic intermediates are at the thermodynamic potential for reversible reduction of carbon-oxygen double bonds. Secondly, Noyori, who won the Nobel Prize in Chemistry several years ago, identified an intriguing aspect of the way in which these catalysts reduce carbon-oxygen double bonds, in that you have a metal hydride and a ligand, that is a nitrogen ligand, and they act cooperatively to add hydrogen across this carbon-oxygen double bond. Now, the reason that intrigued us, so our basic model is if these catalysts work chemically, if we can remove the ketone here and just pull the electrons and protons out, we'd have an electrocatalyst that was operating at the thermodynamic potential for either oxidizing alcohols, using those fuels efficiently, or running it in reverse, dumping protons and electrons into those efficiently to reduce these carbonyl substrates. So why is this bifunctional mechanism important? If you think about how nature attacks challenging chemical problems, like activating something like CO2, enzymes are designed over millennia, and there's usually a constellation of functional groups that act in concert to lower the barriers to any catalytic reaction. And in some sense, this mechanism that Noyori proposed is just like that. And so the logic is, if many metal hydrides are known to reduce CO2, and you've heard of some, these palladium catalysts. But for a hydride to reduce CO2, typically that hydride has to be pretty reactive. And the logic is, if we have a metal hydride and we have this bifunctional mechanism for reducing this bond, this hydride won't have to be as reactive as that one. It will be easier to generate it electrochemically if in the key step of reducing the CO bond, you have this bifunctional mechanism. So that's something we wanted to look at in some detail. And so Kate Waldy in my group and Kristen Brownell, our first approach was to go to the literature, identify catalysts that perform this reaction well. So our first test catalytic reaction is what we call transfer hydrogenation, where an alcohol will reduce a ketone. So we measured the rates of those, and these catalysts I pointed out here, these ruthenium catalysts of Noyori, will do this reaction reversibly, but their rates are rather slow, about 20 per hour or 113 per hour at room temperature. However, this particular catalyst that was derived by Barada does this at about 6 per second. So that was a very attractive candidate. But we don't want to be limited simply to ruthenium or to catalysts in the literature. And so in a parallel program in the group, we're trying to devise completely different metals that will operate like this with more abundant, earth-abundant metals. And so Tomo Seiki, a postdoc in my lab, developed the first molybdenum catalyst that will operate by this kind of mechanism. Now this is generation 1. It's not very fast, right? It's about 0.03 per hour at 50 degrees. And I'll tell you a little bit about this cobalt catalyst. But here's a case where we're trying to expand the repertoire of catalysts that'll behave this way. And with Tom Jaramillo, it's likely that you will never generate a fuel cell with a molecular homogeneous catalyst with these exotic ligands. And so with Tom, we're trying to take some of the concepts we're developing here and use those in heterogeneous systems where similar mechanisms operate, but they'll be more robust electrocatalysts. Okay, so our first generation, we wanted to see this catalyst, which is an active transfer hydrogenation catalyst, will it be an electrocatalyst? And it is. So we can oxidize methanol to formate at about 1 per second. So these are quite good electrocatalysts for oxidizing methanol to formate. Unfortunately, the potential at which it does that at this rate is about 1 volt farther north than we want to be. So the rates are good, but the overpotential should be down here, and we're up at about 1 volt. So that's a problem. Kate Waldy has looked at some of these more active ruthenium hydrides, and now we're starting to see electrocatalytic current with these rates at much lower overpotential. But frankly, at this point, we still are working on this catalyst to show that we're actually oxidizing isopropanol and not other products in the mix. So here's an example of this idea, and right now this is, I would say, a hypothesis, but we noted there was a report in the literature that there was a heterogeneous catalyst, ruthenium hydroxide, on anatase nanoparticles, and they showed that they were catalysts for transfer hydrogenation. And so Anthony, with Megan and Tom, using some of the cells that Kendra had devised in Tom's lab, the idea was if you have a titanium electrode, it will naturally form an oxide layer. And if we could then put ruthenium oxide on that layer, the layer is thin enough that we can get electrons through there, and we would have an electrode catalyst that mimicked the ruthenium oxide on titanium nanoparticles. And so Megan showed that if you make these electrodes, they will catalyze this reaction, the transfer hydrogenation reaction, and they can also function as electrocatalysts for oxidizing isopropanol to acetone. They do it at a modest rate of about 0.6 per hour. And again, the overpotentials are a little high, so this is not the perfect electrocatalyst, but I think is an example of how we're trying to use some molecular concepts we're developing with these exotic homogeneous catalysts to develop new heterogeneous catalysts. Okay, so now how do we activate CO2 with metal hydrides? So Kate Waldy took this ruthenium hydride that I mentioned to you before. Notice it has a ruthenium hydride in one of these NH groups, and she showed that this would rapidly react with acetone to generate a ruthenium isopropoxide. So we could then measure this equilibrium constant and the rate. She also showed that this thing will react with CO2. In fact, you just put an atmosphere of CO2 on top of this solution of this catalyst, you can see the color change instantaneously, very rapidly at room temperature. This thing reacts with CO2 to make this ruthenium formate. And here's where theory came. We wanted to use some theory to try to understand the details of these reactions. And so Srini, a joint student in Chris Chidsey's group, we collaborated with the people at Yale. And then Todd Martinez has recently developed a way of doing quantum chemistry calculations on graphic chips. So my kids can use a computer far more powerful than mine to do FIFA soccer, right? Your graphic processing units. And so Todd has developed this TerraChem, a remarkably powerful computational software that allows you to do these calculations very rapidly. And we could actually measure the thermodynamics, the equilibrium constants, and the free energies, and calculate them and get quite good agreement between the calculated and experimental numbers, giving us some confidence that we had a way computationally to predict how these catalysts would behave, and in fact to understand how they activated CO2. And so a key outcome of these calculations was that in fact part of the reason the barriers to insert CO2 are so low is just this hypothesis that I forwarded to you before, that this ruthenium hydride adds the CO2 at the same time that this NH bond from the ligand stabilizes the incipient anionic charge building up on CO2 as we react it very rapidly. Now, the downside of this particular reaction is that if you insert acetone, this is fast and reversible, exactly as we want. In a catalytic reaction, you don't want any barrier to be too high, and you don't want any well to be too low. And in the case of CO2, both the theory and the experiment suggest that when you insert CO2, we fall into a well that's about 10 kcals per mole lower than our starting material. So that prevents us from catalytically hydrogenating CO2, and this is where the theory came in a really important way. Because these calculations are now so fast, Srini can do the calculations almost as fast as we can do the experiments. Here's the compound that we started with. Notice the hydride and the isopropoxide are very close in energy, but down here in this box, we fall about minus 10 kcals into this well of this ruthenium formate. But in silico, you can now modulate the catalyst and change the ligand and ask, how does that affect, how do we balance the thermodynamics of these reactions? And it turns out if you change this nitrogen, this phosphorus to a nitrogen, now these are both much closer in energy. And so we're quite excited about this because now it's easier for me to draw these structures on the slide, but to make one of these compounds is non-trivial. And even Kate, who's extraordinary, can make almost anything. We're now inspired that because of these calculations, we can be quite confident that this would be a very productive catalyst to go after. So this combination of using this high-powered theory and experiment has really just come to the fore in a way that I think is really exciting. Okay, so the last part, I think we're starting to understand how we can activate CO2 and ketones very rapidly if we have the right type of metal hydride. The question is, how do you generate those metal hydrides efficiently at low overpotential? The typical way is you need a metal that you can protonate. And you typically have to drop several electrons into a metal in order to get that metal basic enough to be protonated. And that's typically very hard. Here's an example from the literature. If you want to reduce hydrogen, protons to hydrogen, you will make a metal hydride that is thermodynamically potent enough to either liberate hydrogen or to react with CO2. But to do so, you typically have to go to minus 1.1 volts instead of about 0.3 volts, minus 0.3 volts where you need to be. So the idea is to borrow another concept from nature. How does nature solve this problem? It has single sites that are doing the chemistry, and it typically has an iron-sulfur cluster that acts as a mini capacitor, where you store electrons in the iron-sulfur cluster, and then once the chemistry happens, it dumps the electrons where you need them. So this is the poor man's way of doing that. Here, the idea is to design metal complexes where you have a ligand, where the ligand can accept an electron. So you don't have to put both electrons into the metal. You could put one electron into the ligand, one electron into the metal at very low overpotential, and then protonate. So that was the hypothesis. And I have to say, to my surprise, it worked amazingly well. So this is a busy slide, but if we start with this cobalt-3, I want to introduce 2 electrons. And this red arrow is the potential at which it's thermodynamically potent enough to either react with CO2 or to generate hydrogen. And what you see is we're putting 2 electrons into this cobalt system at a potential a lot less than we need to be. That's very good news. Okay, and if you look in the dotted line, this is an analogous compound that does not have a redox active ligand. It's harder to put the first electron in, and then to put the second electron in, you have to go to very negative potential. So that was a very promising result. And now if you look at, can we generate hydrogen this way? So this is an active catalyst for the hydrogen evolution reaction. Unfortunately, even though we've put 2 electrons into that cobalt species at this potential, we don't start generating hydrogen until we're at a much more negative potential. So somehow we've got the electrochemistry right. We didn't have the chemistry quite right. And this is where Kate really came to the fore because she was able to figure out what happened. You could put 2 electrons into this cobalt. She could isolate this cobalt compound. And now we're studying this because we don't really know where that electron resides. Did we put both electrons into cobalt? Or did we put 1 electron into cobalt and 1 electron into the ligand? Or did we put both electrons into the ligand? It's a diamagnetic compound right now. We don't know. But clearly 2 electrons went in to make a stable compound. If we put 2 electrons in and 1 proton in, we again get another compound that Kate was able to isolate. But here the problem was we wanted to put the proton on cobalt, but the proton went on the ligand. So here when we're dropping these electrons into these systems, what we don't understand now, unlike nature solved this problem, how do we get the electron to behave in the way we want it once we've stored it into these compounds? We'd like it to store it, to drop it onto cobalt, to make the cobalt hydride, and we've dropped it onto the ligand. Here's, I think, where theory is going to play a really important role. This is a first good generation idea, but I think this ligand is probably not the optimal one that we'll need. So in summary, I think what I've tried to tell you is that our approach has really been to try to understand how you mediate these electron-proton transfers. We need both theory and experiment to help us understand, should we put electrons in first? Should we put protons in first? What are some of the design principles that we need to put into these catalysts to get these to happen fast? Theory is going to be really important here, and I think you'll hear that in Tom's talk next, because it takes some time to test these hypotheses. You have to make these compounds, and without some guidance about which path to go down, it becomes a very frustrating process, but we're really excited about that capability. But I think fundamentally what it tells us is that we really now do not completely understand how to control the communication between when electrons go into ligands, how do they know when to come back and react with the metal? And so that we can solve the problem of putting the electrons in at the right potential and then getting them to do what we want when the metal is actually doing the reaction we want. And related to that is, I think, a more fundamental problem, which is how do we engineer molecular systems to be able to add protons and electrons simultaneously? It's quite well known that if you first have to put an electron in and then have to put a proton in, that is almost always a higher barrier than if you can get them to come in concert. And how to understand that coupling is something that I think we're still far from. So with that, let me thank the people who have done this. Kate Waldy, who's right here, really an extraordinary synthetic chemist and a great electrochemist. Megan Boniato, who's done a lot of the work with Tom Jaramillo on these ruthenium oxide catalysts. Wei, who's doing some cobalt chemistry I didn't tell you about. Tomo, who developed these molybdenum catalysts. Srini, who's been really leading the charge in the theory with Chris and Todd Martinez. Elena, who just joined the program. GCEP for their funding, and thank you for your attention.
Thank you, Bob. Questions? Yes.
Rob Brown, Colorado School of Mines. Just one comment, I guess. You spent some time emphasizing how do you activate CO2. Of course, we could raise its temperature. That would be one way, and electrochemically reduce it in a high temperature solid oxide system that makes use of more perovskite material systems. And I can electrochemically reduce it at very low overpotential quite effectively. And I can do it simultaneously with steam and make myself a nice syngas, which I can then do downstream fuel synthesis. So just another possible pathway that was shown in the other presentation.
Right.
But certainly can be done in other ways as well.
Yeah.
If I could just add to that, I completely agree that there's many ways, many possible avenues, some of which are coupling, they're pure electrochemical, some are pure thermochemical, some are combined. And I think, of course, at the end of the day, what we're going to be most interested in is what's most cost effective. And I think that's kind of unclear until we have some catalysts that can actually do the chemistries the way we want to. And so that's an important part of all of this. But it's a perfectly valid comment. I totally agree.
Yeah, so the thermodynamics obviously change at different temperatures, right? And that can be an advantage. Our focus has really been to think about very low temperature things to really understand the barriers to these processes and to investigate other strategies to do it that would be different from the high temperature. At the end of the day, I think Tom's exactly right. It's not clear that a low temperature process is necessarily better than a high temperature process. But to understand how to do it, I think, is really where we're lacking in terms of how to do it really fast.
It also gives more possibilities. For instance, if you're coupling to a stable source like geothermal or nuclear, then sure, running something at 800 degrees C is no problem. You can maintain temperature. But if you're trying to couple to something that where literally as the wind blows or as the sun comes up or comes down, then it might be, these temperature cycles might be tough for some technology. So it also depends on what source of electricity you're using to drive these things.
Yeah, great.
Wonderful. Any more questions? Yes, in the back.
Excellent talk. Thank you very much. I just want to make a comment that many environmentalists don't quite understand something about all this. Let's say carbon neutral fuels, is that there's not enough oxygen in the air left since photosynthesis began about 2+ billion years ago to burn all the hydrocarbons that are stored underground. So we have to recognize that obviously anything that we do to create a fuel to run a plane or so forth in the future, it does have to be carbon neutral.
Yes, I agree. I mean, I think the lesson from what we've heard in all the talks today is that the inertia of our past success should not lead us down the same path, right? And while burning fossil fuels and using the available oxygen to do so has gotten us to where we are today, it's not likely we're going to be able to continue to do that indefinitely.
Okay, time for one last quick question, if there is one. Over here, yes.
Are there any excited states you could work with in CO2, such as using a CO2 laser to pump it?
That's a really interesting idea. And in fact, I think in a lot of the photoelectrochemistry, where you imagine, as Tom pointed out, where ways you might not separately couple the generation of electricity in a photovoltaic and then use the electricity, but where you're simultaneously using light. And so there's a lot of really exciting work of doing that, not only to make CO2 more reactive by going to a photoexcited state, but making the catalysts more reactive and changing their selectivity by adding light to them. And so all of those strategies, I think, are really intriguing.
Okay, great. Well, with that, let's thank Bob Weymouth one more time. Thank you.